So this is loci in the complex plane. This is part 3. In this one we're going to run through a couple of different types of loci and just show you one example of each and how we convert them into Cartesian equations and how we draw them on a set of axes. I'm going to jump through this quite quickly because I'm hoping by this point you've started to get the feel for converting into Cartesian equations. A lot of what I'm doing is very similar, and I just kind of point out the things that are a bit different. So the first one we're going to look at is where you've got almost the same as the perpendicular bisector one, the equation of straight line, but this time you've actually got a number at the front, and that number changes everything. That number actually will make this into a circle again. We'll see why in a second. So the way we do this one is the same as all. Then we plug in our x plus I, y in terms of our z, and we group our real and imaginary terms. Do that as 2 steps, do it as 1 step, whichever you do, make sure you do it right. We're now going to take this and do the modulus, so we're going to square the real part, square the imaginary part, square the real part, square the imaginary part, and then I'm going to put the square root signs in. Now the reason I'm going to do that now is because that 2 there hasn't been squared yet, but when I now square to get rid of this square root, it will become squared. And the most common mistake in doing this is to not square the 2. Most people will just go from here, square this, but then leave the 2 unsquared. So that's something to be careful about. Hopefully you can see what I mean. And then we're going to expand this side. To expand this side, well, I would do it in more than 1 step. Let me just cheat. I'm looking at another bit of paper where I've previously expanded this already. You know, I would do it now, expand that bit there, and then times everything by 4. Oh, this is a minus 10 x plus 25 plus y squared. Okay, so you should get something like this. We can now cancel some things down. So for example, the y squared here is going to cancel with a 4. The x squared here is going to cancel. Those are the 3x squares and 3y squareds. Oh, the minus 10x, that's going to cancel over here and give us a minus 14x, right? And the 25 is going to cancel with the 36 to give us an 11. So this side left with nothing, and this side we've got a 3x squared, and I suppose it's what is 3y squared here, haven't we? There we go. Okay, so now we've got the equation for a circle. It's just not written in the best way. To do that, we've got to complete the square on it. So my advice is these 2 numbers here, they're often the same. If they are, then the best thing to do is to divide by them to get rid of them. The other side is equal to 0, so that's an easy thing to do. So divide by 3, all 14 over 3x and 11 over 3. Not the nicest of numbers, but you have got a calculator, and 0 divided by 3 is still 0. Now we're going to complete the square. Now the y bit's already done because there's no y term, but here we've got an x squared term and an x term. So to complete the square, we take the x term and we half it. So half of 14 over 3 is 7 over 3, just half the 14. And then we square it, right? The problem with doing that is we'll still get the x squared minus the 14 over 3, but we'll get another term. So we've got to take away, it doesn't matter what sign is here, we always take away this thing squared. That's because no matter what sign is here, when you square it, you always get a positive number. Now we can take away that positive number, and this will be the same as this bit. So we're going to add on the 11 over 3 still, because that's still there. We're going to add the y squared on it as well. Keep going. This bit here, we've got to shift the other side and add them together. You've got a calculator, so you can do this, or maybe you recognise it's going to be 33 over 9. Either way, this is going to be equal to 16 over 9 when you've moved the other side and taken them away. Now, what I'm not trying to do here is blind you with the quick maths, because actually I'm looking at, just off the screen here, there's a bit of working out when I've done it already, yeah? So I'm not being a genius, you're not trying to do this fast, I'm just trying to condense it down so you can see more succinctly what I've done. The bits that I wanted to really pay attention to are right at the top here, when we've done this square, the most common mistake is not any of this calculations down here that maybe looks impressive, but that 2 not being squared to be a 4, because people forget when you do the modulus, you've got to square root the real part plus the imaginary part squared, not just do them squared. That's the bit that I want you to focus on, that 2 turning into a 4. If you do that, then you're probably going to get the right answer. Down here, though, we can see now that this actually is a circle, because we can see that it's got centre, well, it's awkward up these backwards. It's got centre 7/3 on the x and a 0 on the y. That's the centre point. And here, this is a radius of, well, the root of 16/9, which is 4/3. So I suppose, actually, we could write this in the form, z minus 7/3 equal to 4/3. But don't worry too much about that, because that's not really here or there, is it? There's no easy way of taking that and getting to that. In fact, the only way of doing it really is to go through the Cartesian form. So, interesting there. That's one example. Again, the same process the last 2. Exactly the same process as the last 2. I would like just to mention one other type. I think we have time to mention it on this video. So, let's consider it over here. What about if we have something like, not the modulus, but the argument of z equal to a number? What would happen then? Well, this is actually quite easy to see just graphically. You're looking at all the z values that have a modulus, so I have an argument of pi/4. So all these numbers along here, I've got an argument pi/4. These numbers here don't. These numbers have an argument of minus 3 pi/4. So it's only this thing here. It's called a half line. Yeah. I could do other ones. You could do argument of z is equal to pi/2. It would just be the positive y-axis, because that's got an argument of pi/2. And you could do more interesting things like the argument of z minus 3 is equal to, I don't know, pi/3. That one there is a little bit more interesting. This time we've got to start at 3, and we want an argument of pi/3. We could also do things like the argument of z plus 2i is equal to, I don't know, 3 pi/4. And that would be okay. We'd have to start at not 2i, but minus 2i down there. Let's just go a page. Minus 2i down there. And this time we measure always from the positive x direction, even if the x-axis isn't there. And we do 3 pi/4, which goes right around to here. 135 degrees, I think. There we go, 3 pi/4. And it's that half line projecting away in that direction. And that's how you draw these. Now, it's really rare for them to ask you to take these equations and to convert them into Cartesian equations. In fact, I don't think it's technically on the syllabus. I wouldn't put it past anyone to ask you, because that's what examiners are like. It's not too hard to do. And we will talk about that in either in lesson or the next video. This pretty much covers now all different complex number loci that you generally see. So hopefully you guys will be able to get on now and answer some of those questions. Good luck. See you later.